All right, we are back. Section 12.4, testing the significance of the correlation coefficient. So we saw in the last section that correlation coefficient R tells us about the strength and direction of the linear relationship between the explanatory and response variables. However, the reliability of the linear model also depends on the number of observed data points in the sample. So we're looking at the reliability of the linear model, right? Because the more data points we have, the better our estimates are going to be, right? Because if I'm building a linear model and I only have 3 data points, right, then that's not very helpful, right? Because if I draw here's 1, 2, and 3, and I draw my line, well, that's great, but what if my other data points were like way out here somewhere, and I just didn't collect those data points? Then that's not very helpful. So the more data you have, the more reliable your linear model is going to be. Okay, so in order to determine if we do have enough evidence to support a linear relationship, we can run a hypothesis test. So we're going to test the significance of the correlation coefficient. So here we're looking at the difference between the population correlation coefficient, symbolized by the Greek letter rho. So this is how it's spelled in English. It looks like a P, but it's kind of rounded, so it's kind of like that. So that's rho. That gives us our population correlation coefficient, which is unknown, right, as a lot of these population data are. And then R, of course, is the sample correlation coefficient that we can calculate ourselves. All right. So note, if R is significant and the scatter plot shows a linear trend, the line can be used to predict the value of Y within the domain, right? So we're not extrapolating beyond that. If R is not significant, or if the scatter plot does not show a linear trend, the line should not be used for prediction. And if R is significant and if the scatter plot shows a linear trend, the line may not be appropriate or reliable for predictions outside of the domain of observed X values. So it's basically just what we were saying last time. So we can use it to predict values within the domain. We should not be using it to predict values outside the domain. And if it's not significant, then we shouldn't be using the line at all. Okay? So our null and alternative hypotheses are right here. So the null hypothesis is that there's not a relationship, right? So status quo, we just assume, no, there's no relationship between them. And then the alternative hypothesis is that there is a significant relationship, linear relationship between these two. So notice that this is a not equal to. So what that tells us is this is a two-tailed test. Okay, and so that's going to come into play when we're actually testing our values. Right, and remember, when the R value, in this case rho, is about 0, that means there's very small or no relationship between the variables. So here's our hypothesis test. So, as always, determine the null and alternative hypotheses, determine your alpha value, and then they're going to use the p-value approach. So in this case, so let me show you how we're going to do this. We are going to be using a t-distribution for this, and our degrees of freedom, because we do need degrees of freedom for a t-test, is going to be n minus 2. Okay, so again, from up here, it's a two-tailed test, and it's a t-distribution with degrees of freedom n minus 2, and our test statistic is going to be calculated using, so t0 equals r times the square root of n minus 2, so the degrees of freedom, over the square root of 1 minus r squared. Okay, so 1 minus r squared. Alright, so that's the formula we're going to use to determine the test statistic. And then we're going to run our our hypothesis test the same way we always do. So we get our alpha value, we compare it to the p-value, right, corresponding to this test statistic. And if the p-value is smaller, we reject the null hypothesis. If the p-value is bigger, then we do not reject. Okay, that's kind of what it says right there. So using the same example that we've been using, test the claim that there is a significant relationship between the starting drilling depth and the time it takes to drill 5 feet. So we saw in the previous section, right, when we looked at the coefficient of determination, we said that the line has about 60% explanatory power, which indicated that there was a pretty strong relationship between the two variables. But now let's see how good this line is at explaining that linear relationship. So we need our hypotheses, so H naught and H1. So our null hypothesis is that there is not a significant linear relationship. And our alternative, of course, what we're trying to find evidence for, is that there is a significant linear relationship. Okay, so that's what we're looking for here. All right, so let's see what we got here. So we know the degrees of freedom is n minus 2. So if you go back into the table, so way back when, that data set, there were 12 data points in there. So there were 12 in the data set. Minus 2 is 10. So we have 10 degrees of freedom. The test is two-tailed. Okay, so in our alpha value, it doesn't specify. So when it doesn't specify, we typically just go with 0.05, right? So 5%. So then our alpha over 2 value is 0.025. And why are we doing that? Because it's two-tailed, right? So each tail of this relationship, this tail is going to have alpha over 2, and then this tail is going to have alpha over 2 as well. All right, and then our test statistic, so T naught, that is R, so 0.7728, which we found in the last section, times the square root of n minus 2, which is 10, over the square root of 1 minus 0.7728 squared. Okay. Which then, if you look at Desmos, I went ahead and already calculated this for us. So there we have it right up there. So about 3.85. So about 3.85 for that test statistic. So for our p-value, so that's going to be the probability that t is greater than or equal to 3.85. All right, and that's going to give us half of the data, but we're just comparing it to alpha over 2, so half of alpha. So that'll be fine. Okay. So let's go find this on Desmos. So we're using the t-distribution, so that's going to be t-dist, and then put inside the degrees of freedom, which is 10. And there's our curve. And I want the cumulative probability above 3.85. And there we have it. So it's about 0.0016. So this is 0.0016. Compare that to the alpha over 2 value, and that is less than 0.025, right, which was alpha over 2. So what does that tell us? Well, if the p-value is smaller than the alpha value, then that tells us that we can reject the null hypothesis. Okay, so what does that mean? To reject the null in this case tells us that our initial assumption of there not being a significant relationship does not appear to be correct. It looks like that there is a significant linear relationship. So let's go ahead and state that in our appropriate wording. So we say there is sufficient evidence. Again, it's not proving it, right? It's not conclusive that there is strong linear relationship, but we have enough evidence to suggest that there is. So there is sufficient evidence to conclude there is a significant linear relationship between starting depth, right, of the drilling, and the time to drill. So the time that it takes to actually drill. Okay, so we are able to see here that there does appear to be a significant linear relationship found using our hypothesis test. So that kind of backs up the data that we saw. All right, and that's it for section 12.4. So a pretty short one here.